Thank you so much for the presentation. Well, I'm very excited to share with you this research. Basically, it was the last contribution of my PhD, so it's a wonderful way of finishing this journey. So I'm really happy. This research was conducted or was supervised by Marlon Dumas and by Oscar Gonzalez from the University of Tartu and University of Los Andes in Colombia. Well, the title is kind of long, so I'm not going to repeat it again. The idea is that we will give some kind of context first. So, it's not working now. Well, business process simulation is a technique that we will know like from some time ago because it's been around there like for a long time. It's been there because it's used mainly for evaluate, is a way of evaluate business processes, especially in the phases of design, right? But now, simulation is being again in the focus of one of these new concepts called digital twin. The idea is not only to support the decisions in the design steps, it's more about to support the decisions in operational level, in tactical level. So it needs some, let's say, insight. Why? Because in general terms, simulation is not widespread adopted. Why? Because there is some faults especially in the first steps, in the designing of simulation models. Because in the traditional way, these models have been designed, guided by human experts, right? So they conduct interviews, they know how the process works, or they think how this process works. But the thing is that this is a process that is really prone to human errors, as well as time-consuming, because fine-tuning a simulation model is not easy. It really needs the knowledge of the engine, the knowledge of the process, so it's time-consuming. It's not so easy to have a really good simulation model. Sometimes the parameters that are discovered are not realistic, and this is another problem in the designing steps. And finally, some execution paths are left aside. That is because maybe the expert doesn't know completely the process, maybe it's something intentional because you want a very simple process, but the thing is in the final step, the model is not completely accurate, right? So all these challenges in the creation of simulation models end up in that the adoption of this technique is sometimes disappointing for many users. But fortunately, we have data that we can extract for enterprise information systems for create our simulation models using process mining techniques. So the question here is how to automatically create accurate business process simulation models based on data extracted from enterprise information systems, right? But before to answer this question, we want to give a step back and have like a broader perspective about what is a simulation process, right? A simulation process is a generative model that is able to generate traces that resemble the behavior of a real process that is in execution, right? So that doesn't mean that it's probable that there is many other generative models that we can use for generate even logs as well. And if we check in the literature in process mining, we can find basically two big families. One, the first one that we will call data-driven simulation is, let's say, a new version of a traditional approach. What we want to do is take process mining techniques and even log and extract all the parameters of the simulation model. We will start with a VPN model, then we will enhance this simulation model with probabilities, resources, and all the perspectives that we need for the model, right? But we have another approach for generate even logs, and it's something that in the last years has been taking like a lot of movement. This is deep learning, and it's been applied in predictive process monitoring, right? The idea is that we can take the data, use a black box model, a deep learning model, and learn from this data and reproduce the event log. So this is a different kind of generative model. Both of them have very different characteristics, starting from because the data-driven simulation models are white box models. They are really easily to use in the what-if analysis. You can modify everything, you can see what is modifying, and you kind of expect some explanation about the final results, right? The problem is that they are not entirely able to reproduce the human behavior. It's very complex for these kind of simulations, and they are based on a discrete event simulation that is kind of robotic, right? The deep learning models on their own, they are black box models. You cannot modify what the rules that they are inferring from data, right? But they are very accurate. So the question here is, or the hypothesis that we have, is that actually we can combine both of these approaches and create a technique that is more accurate and still can be used for reproduce the current behavior of the process, and as well some what-if capabilities. Maybe not in all the extent, but in some use cases we can use still in what-if analysis. So having this in mind, we propose Deep Simulator. Deep Simulator is basically the tool that is supporting the method, the hybrid discovery of simulation models, and it is composed of 3 phases. In the first one, we are basically generating sequences. In the second one, we are enriching these sequences with start times, and in the third one, we are predicting times. So the first phase basically is discover an stochastic process model, right? We discover a VPN model, and then we replay the event log, we enhance this model with probabilities, and we can generate sequences that are present in the log and that maybe are not present in the log as well. So we can generate sequences in here. This is like the part that we are taking from the data-driven simulation, right? Just sequences of activities. In the second phase, what we are doing is enriching the sequences with the start times. For this, we are using a time series decomposition. We are forecasting basically the series of number of cases generated by day and by hour. We are trying to we apply the Facebook Prophet model. And this is much more, let's say, adequate for represent the generation of cases than the traditional approach. And in the last step, we are predicting the processing times and the waiting times using deep learning. These models are able to learn not only the information about the current execution, they are also aware of the execution of all the traces that are executing in the same moment, because they use intercase features, they use contextual features. So in here, we are really predicting all the times, and we are trying to not reproduce all the detailed elements of the human behavior, but we are capturing this complexity, or the deep learning models are capturing all the complexities that are in data. We test this approach with 10 event logs, real event logs, synthetic event logs that are private, that are public event logs, all of them with different characteristics in the number of traces, number of cases, time variability. So the idea was as well to test in a small and large extent this approach. And we proposed two experiments. The first one was to reproduce the current state of the process, the as-is state of the process. So what we did was basically execute a DDS approach, we called CMOD, the deep learning approach, just generative models, and the deep simulator. We use the same data for the 3 models, start to generate them, and then we measure the generated model against the ground truth. Basically, what we found in here is that the deep simulator outperforms all the previous approaches, especially the DDS approach. So this means that deep simulator is able to reproduce more faithfully the behavior of the process in the current state. That's our base for, let's say we have now a digital twin. It's our base for start to perform what-if analysis. In the second phase, we wanted to test the what-if capabilities of the deep simulator. So we proposed two scenarios. In the first one, we are modifying the arrival intensity of cases. What we did was taking an event log, in this case was the BPI 2017, we split in 6 batches, we reduce in the batch number 2, 4, and 6, we reduce the arrival rates, we modify this data, and then we train the model. And we have 2 versions in here, one in which we just reduce the demand in these 3 batches, and another one in which we alter as well the waiting times, because of course if you have less arrival rates, maybe you have as well less waiting times because you have more availability of resources. So it's a complex scenario, and the idea is to see if the deep simulator is able to reproduce these variations in data. In the second scenario, we are testing a different what-if scenario. Let's say it's a more challenging scenario for deep learning models, because we are adding a never-before activity, never before observed activity in the data. This is very complex for deep learning models. They are not able to reproduce something that is not in the patterns they are observing. So in here we start with a simulation model. We generate a full event log with this simulation model. Then we remove one activity of this model. We generate another event log that doesn't have that activity, and then we add that activity to the deep simulator model that we trained. So we are not retraining the model. We are just giving the option to generate an event log from data that doesn't have that activity. And then we compare both versions, one of the deep simulator trained with the full event log, and then one with the model that was updated. In our results, what we have is that basically in the first scenario, deep simulator was able to reproduce the arrival rate variations with great precision. So even it overpasses in almost all the scenarios to the data-driven simulation approach. So we can say that this approach is able to reproduce this kind of what-if scenarios that are really complex. And in the scenario number 2, we in here have, like, let's say, some troubles, because as we expected, the deep simulator and the deep learning models are not able to reproduce very faithfully this kind of introduction of new activities, right? But there was some other observations that were like giving us some expectancy for future work. So what is our future work? Well, what we can do, or what we expect, is use mechanisms for introduce these new activities, these on-scene activities in the predictive models with more precision. Models that are really focused in embeddings of activities, models like word-to-vec or transformer models. The second possible future work is generate events that include resources and some capabilities that deep simulator has that are not present in previous approaches, is that we can as well generate data that is not only the basic data like activities, resources. Now we can reproduce as well all kind of data that we can observe from the event logs. So it's an extended capability, and it's a way of extending this work. And the last future work is support a broader range of changes, of course. But this is like a new paradigm for simulation. So it's not only simulation based on one model. We can basically, for each one of the components of the simulation, use a different type of model that is precise, and then we can use it for reproduce our behavior of the process. So this is for the moment. I think I was on time. So yeah, questions.
Thank you very much also for the excellent time management. I guess there are already some questions.
Congratulations for your very inspiring presentation. I was wondering that one of the aspects which is mentioned as a drawback for simulation is the individual variability. I mean, usually simulation models don't account for resting times and people which are more productive than others, people that want to make coffee breaks often and so on. Mm-hmm. So do you believe that deep learning, such a deep learning approach could be used, for instance, for training based on, imagine that you are in a company where you have lots of data, personalized data on resource A and B and C, so not the role itself, but the persons, and then you don't have the problems where the RGP, Data Protection Act, but then you can use and train your model to the behavior of person A, B, and C, so that your simulations can be more close to reality and, I would say, useful for the employer.
Mm-hmm. Well, yes, indeed, it is very complex for an user, like start to use these kind of techniques, right? But the idea behind of all this research is like it's going to be kind of transparent for you. You just have to be aware of creating a very clean event log, right? And you give it this to the approach, and he will be in charge of the rest, right? Of course, there is like a venue for future work, like for example, for these what-if capabilities, we have to provide to the user some easy way of interact with the tool and say, okay, I will reduce the demand or I will create an increasing demand, for example. That is something that it has to be work in like a different core, let's say. It's more about the interaction with the user. Yeah, I think that's something that is for future work. Yeah.
Maybe also in this line, so if companies are supposed to use this, at which time would you recommend it? So they have collected logs or so, and then they do the what-if analysis. Maybe the system is running, but in parallel or so. Could you also like synchronize and harmonize this?
Yeah, well, in a principle, in this stage is more an offline work, let's say, once you have data from cases that have been finalized and they are completed, you can use for discover these kind of models. But of course, the idea is that after having an initial version, you can maybe use it in a streaming way, right? With the models that you have trained. But that includes much more work, like how to update your models continuously for being able to reproduce new changes in the paradigm. And each one of the components of the simulator have to adapt to these new changes, of course.
Mm-hmm. Mm-hmm. Yeah, I see. More questions? There's one.
Okay, thank you for your presentation. I have a question regarding your approach compared to approaches where the human is still involved, because you really go for the approach where we don't need the human anymore. Maybe a first open question. Do you see limitations to that approach, that you don't have an expert involved anymore? And secondly, very often simulations, in my opinion, are used to explore situations, to make strategical decisions, tactical decisions, where you explore situations that you have not observed before in the data. Imagine instead of people going to one help desk, you separate the help desks and certain questions go one help desk, the other one, and you want to explore that. So if you don't have any data about that in historical data, to what extent do you think your approach could deal with these type of questions?
Well, by let's say in this version of the tool, we still can explore some of these unseen behaviors. That's why we wanted to make like a hybrid technique, right? We can as well represent, let's say, changes in the structure of the process, like change order of activities and these kind of changes that still the traditional approach can reproduce as well, right? Of course, there is use cases in which the tool is not going to be able to reproduce these unseen scenarios, right? Like a complete change in the paradigm that is happening in the business, right? But it's something that actually the current simulation technique, discrete-driven simulation, is not completely aware of it. You really don't know if the simulation, the discrete-driven simulation, is being really precise, neither. Why? Because what is in the bottom of the discrete-driven simulation is just one assumption, and is, for example, that your resources are basically robotic. You are finishing one activity, and you are going and execute the next activity. So, in this sense, we need as well to face these approaches. It's not something ended.
If I can add to that, because I found that a very remarkable, you mentioned it also in your slides, I found it very remarkable, because I think when you have a domain expert and you say, well, I assume all my resources are equal and they just do robotic, they're like robots, it's a modeling decision. There's no reason why you could not model different kind of resources. You say, well, I have two types of people, and some people take a lot of coffee breaks and the other ones don't. You can actually implement it in your model. So I'm not fully sure that and that's the point, I think, when you exclude the expert, the domain expert that usually builds the model, that kind of information is lost because you don't have it in the data. Imagine you hire, and you only have postdocs in your team, and you're modeling the process of publishing, and suddenly you decide, let's start hiring pre-docs. They will work differently, but you have no data about pre-docs in your data. Mm-hmm. But a domain expert could say, well, but we can expect the pre-doc to take more time to write a paper.
Yeah.
So I'm just wondering, let me end with this question. Have you tried to compare your approach with an approach where the model was created by domain experts? You will win in time, for sure. Your model is much faster. But if you talk about accuracy, I think that's the challenge you have to prove, that your approach reaches accuracy levels comparable to a model created by a domain expert. So my question, have you been able to do such experiments yet?
Yeah. Actually, of course, in the beginning of the exploration of this technique, we had to make validations. I mean, we are not arguing like the technique is much, like 100% more exact than having an expert, right? What we are saying is not always possible to have an expert for creating a simulation model, right? And you have to do it as well fast. But as well, having an expert, you cannot be even 100% sure that what is in the model is perfect. So it's not only, let's say, a weak point for a simulation or for every technique that is based on data has the same, like, let's say, weak point, right? We still doesn't know if everything that is in the data is completely enough for describe the complexity of the phenomena, right? So it's a fault that in every data-based technique we will found, of course. And the idea, at the very end, we don't want to exclude completely the expert. We want to involve him like someone that can, of course, possibly add or proportionate the base model, let's say a business process model, and from there we can use the rest of the tools for enhance this model. We can do it actually with Deep Simulator because we can just change the phase one and add one expert, and this expert is gonna give you the base model, right? So yeah, of course, it's something that has to be taken into account. Yeah. Thank you.
Yes, thank you very much. Maybe also in this line of argumentation, so it's not only like human tasks that could be modeled, but tasks are so much, they have a lot of functionality, yeah? There's life cycles, everything. Could this also be integrated and explored more to gain more information from that? I mean, the activity starts somewhere, could be suspended, could be there's a service maybe invoked by the activity that does something and all these things. Is this also a line of research that could be followed here?
Yeah, of course. The advantage of having models like deep learning models is that whatever data you have, you can as well ingest, extract patterns from there, and you can start to reproduce it as well, right? So yeah, of course, we want to extend the simulator in that way.
Okay. Yeah, I think it was already very nice discussion. Then we are just a few minutes early, but I think this doesn't matter. Then let's thank Manuel again for this discussion and his talk.